Hi guys, this is Dr. K. What we're going to do is analyze rate law data. This is the second part of a series. And what we're going to talk about is how you actually go about analyzing what's called pseudo first order reactions. Now, I should point out that in the experiment that you did at the beginning of the semester, this was probably a better way to analyze the data to get both the rate law and the rate constant for the reaction. And I want to encourage you, if you get a chance to go back and analyze the data, to do that using the method I described in here. Feel free to update your formal report to reflect that you reanalyze the data and obtain new results. So first of all, what I want to do is do three things. I want to talk about what's pseudo first order. 2, what does the data look like when you collect it? And 3, what do you do to analyze the data to give us the rate law? So let's think about what this means to be pseudo first order. Let's say I have a reaction that's second order overall. It's got two components, A and B. So think about a reaction that has A and B, and during the course of a reaction the concentrations of both of them are going down. And let's assume you start with both having the same concentration. If the stoichiometry is 1 to 1, when A dropped by half, B would drop by half, and as a result, because both of them are first order, the reaction rate would drop by a factor of 4. This is the idea that it's second order overall, first order in A, first order in B. Now, in a pseudo first order reaction, what we do is we keep one of the concentrations constant. Now there's a couple of tricks that you can use to do this. You can do it with a catalyst because the catalyst concentration isn't used. You can add the reactant continuously to keep its concentration the same. Or what people do most of the time in these kinds of situations is make one of the concentrations relatively high relative to the other. For example, if we keep the concentration of B very high, then during the course of the reaction, only the relative concentration of A is changing. We'll talk about this more in the next slide. But what this does is it takes a second order reaction and makes it appear to be first order. This makes our kinetic analysis, our rate law plots, a lot easier to deal with. So let's talk about the way we would set up this experiment in that last way, where we make one of the concentrations high relative to the other. You notice I have a reaction of A plus B. And what we're going to do is we're going to run these reactions and measure the concentration of A. In your experiment, it was the dye, as a function of time. So the concentration of A as a function of time. We don't necessarily know what the stoichiometry is. Let's just assume that it's 1 to 1. Let's say we run this reaction to its completion so that at the end of the reaction 0 A is left. And let's just look at experiment 1 as an example. If all of the A ran out, then 2.5 times 10 to the minus third molarity units of A would disappear, and so, because the stoichiometry is 1 to 1, so would B. B would drop by the same amount. So if all of A reacts, B goes to being 0.8 minus 0.0025, that's the 2.5 times 10 to the minus third, and for all practical purposes the concentration when rounded is still 0.8 molar. By doing this, this is how we set the concentration of one of the reactants to be constant, and this will cause the reaction's rate law plot to reflect only the concentration changes in A, and we'll be able to do a kinetic analysis on the concentration of A and figure out what the order of A is. So we have 3 experiments here. So let's look at the 3 experiments. We have an experiment 1 and 3. 1 and 3, we change the concentration of B, but not the concentration of A. So for measuring A, we expect the signals to start at about the same concentration. If you look at experiments 2 and 3 here, you'll notice the concentration of A changes, but the concentration of B is constant. So run the experiment, and this is what the data looks like. So you'll notice experiment 1, that's the blue dots here, and experiment 3, that's the red dots. In experiment 1, the concentration of B is higher than the concentration in experiment 3. So what happens is it appears that the reaction is faster. That is, the concentration change versus time is much faster for experiment 1 versus experiment 3. So we know there's some dependence on the rate of the reaction with the concentration of B, and I'll show you how to analyze that. On the other hand, if you look at experiments 2 and 3, now you notice I regraphed 3 here. So 3 is on the graph as red, and you notice it starts out here. That's about 2.5 times 10 to the minus third. This is about 2.5 times 10 to the minus third. So just graphed on a different scale. And if you remember experiment 2, the concentration of A was doubled, the concentration of B was held constant. And this is what the concentration versus time plots looks like. So when you go to analyze this as rate law plots, you would do it just like we talked about in lecture. You take the concentration versus time and you look at it. Well, these are not linear, so it's probably not zero order. You look at the natural log of concentration versus time to see if it's linear, or 1 over the concentration versus time to see whether or not it's linear. I've already done that in this experiment, and the data for experiments 2 and 3 look like this. So what I've done is, this is experiment again 2, and this is experiment 3, as it shows here in the legend. Okay, and I took the natural log of concentration, that's over here, versus time. You notice they make very nice linear plots. And two things to notice. For experiment 2, where the concentration of A was higher, it just starts at a higher intercept. But the slopes, these K values, are exactly the same. Remember, the K value is the slope, or related to the slope. So what you see is changing the concentration of A during the course of this reaction, that is, having A start out at higher or at half its concentration, didn't affect the rate of the reaction. However, because it's linear, we at the very least know that the rate is proportional to K times the concentration of A to the first order, because this is a first order plot. Now let's look to see what happens when we change the concentration of B, and the results are very different. First of all, you notice how the slopes of these two lines change. There's that slope and that slope. Certainly in experiment 1, the slope is higher. If you do a natural log of concentration versus time, you'll notice what you have is that the slope is actually changed, unlike the experiments that we looked at before. The reason this changes is because the concentration of B being constant, we have an apparent rate constant for this reaction, which is actually just K, the actual rate constant for the reaction, times B. And B has a power associated with it, which is 1, 0, 1, 2, or 3. In this case, we know it has to be at least 1. I'm just going to call it N for now. So let's go back and analyze the data. First of all, experiments 1 through 3, all the reactions appear to be first order. That's because what you're looking at is the concentration change of A versus time, or the natural log of A versus time. And we've determined that this means the concentration of A is to the first power in the rate law. Now for experiments 1 and 3, the apparent rate constant varies with B. So now what we have to do is we have to analyze this. If you look at the apparent rate constants, and this is just a retabling of the original data here. This is the data that I gave you before, and these are the slopes from the graphs. The rate constant for 1, the apparent rate constant for 1 is equal to K times the concentration of B in reaction 1, divided by K times the concentration of B in experiment 3, but they're both raised to some order which we have yet to determine. If you simplify that, the K's will cancel out, and what you find is that the ratio in apparent rates and the ratio of concentrations will be proportional to each other when raised to the appropriate value for N. So K1, that's here, and K3, that's there, when divided give me a factor 4, and the concentrations of B in those two experiments are actually going to give me 2. So what I know is that 4 is going to be equal to 2 to the N, and hopefully we know that then N is equal to 2, and so this reaction is second order in B as interpreted from the slopes of the reaction plots versus time. So what I can write then is that the rate law of the reaction is rate is equal to K times A times B squared. So just a quick summary. Experimental conditions. Setup conditions so the concentration of one reactant is relatively constant. In this case, we chose what we called B. Now, in your experiment that you did in experiment 1, that was the bleach. The bleach was approximately 1,000,000 times more concentrated than the dye. But there are other ways to do this. One is the high concentration. That's what we talked about here, and that's what we do in our labs. You could also test the effect of a catalyst. The catalyst concentration can be held constant because the catalyst isn't consumed during the reaction. However, you can still vary the concentration of a catalyst and look at the change in the apparent rate constant. The other thing that you can do is you can constantly add the material or set up a clever reaction or two to regenerate the reactant so its concentration stays constant. Finally, when you analyze this, you use rate law plots for determining the order of the substance whose concentration you allowed to change. In this case, that was A. And then what you do is you look at the slope of the rate law plots in order to determine the order of B. That is, you look to see how the slope changes as a function of concentration, and then you determine the order from that. So I hope you found this useful and are going to be able to go back and look at your data and analyze it for the rate law for your reaction and get a specific rate constant for the conditions in which we did the reaction. So good luck.